Hello guys, and welcome to today's lesson. In this particular lesson, we are looking at logarithmic functions. In this lesson, we are looking at logarithmic functions. In our past tutorial lessons, we have looked at polynomial functions, rational functions, and we have equally looked at some of the elements that are involved in these functions, like the domain of definition, the limited bounds of the domain of definition, the vertical and oblique asymptotes, the horizontal asymptotes, the intercepts, the variation table, and to sketch the curve. Please make sure that you've subscribed to this channel and follow this video to the end, as a lot more is on its way. So these are some of the functions we'll be looking at in this special edition of logarithmic functions. We will look at logarithmic functions with absolute values and logarithmic functions with brackets, and we see how we can actually study the variation of these functions. Welcome once more to the GCE Math panel, Math 24 Super Channel, and the GCE Preps platform. Today, I am your host, Dr. Miles. So we begin with this first question, which is studying the curve of the function g of x is equal to lim x plus 1 over x minus 2. So the first thing is to get the domain of definition. And for a logarithmic function, this function is defined if what we have in this bracket is strictly greater than 0. 1, because the log of negative numbers do not exist, and the log of 0 does not exist. So what we have in this bracket should be strictly greater than 0. And secondly, the numerator should not be 0, because if the numerator is 0, what we will finally have inside this bracket will equally be 0, and log 0 does not exist. Equally, for the denominator, x should not be equal to 2, because it will still make this function undefined. So here, x should not be equal to 2, that's for the denominator, and the numerator, x should not be equal to negative 1. Anyway, since this is an inequality, look at it very well, this is an inequality, so these are just the boundary solutions. Now we have to test and see the regions where the domain lies. Does it lie below negative 1, between negative 1 and 2, or above 2? So we test. If we take a point between negative 1 and 2 and test in this expression we have written here, or this equation, inequality rather, we will have, for example, let's use 0 for this region. 0 plus 1 is, the numerator is positive. For the denominator, 0 minus 2 is negative. Positive divided by a negative number is a negative number, and a negative number is never greater than 0. Which therefore means that the region between negative 1 and 2 does not satisfy this inequality. That is why we have this x here. And these circles here are not shaded, implying that negative 1 is not part of the domain, and 2 is not part of the domain. Now let us test the region below negative 1 and the region above 2. Note that in inequalities, we work with regions, unlike for equations that we work with numbers. For inequalities, we work with a range of values. So let's test the value below negative 1. If you take any number less than negative 1, for example, negative 2, we have negative 2 plus 1, the numerator will be negative. And for the denominator, we have negative 2 minus 2, that's negative again. And negative divided by negative is positive. So this region satisfies this inequality because a positive number is greater than 0. Then, if we take any number greater than 2, of course, this region equally still satisfies. If you make a mistake at this step, listen attentively, guys. If you make a mistake at this step, then you have missed the function completely. That is why I take my time to explain very well what is required at this step. So the first thing, for this logarithmic function that has a rational function in it, this is some sort of a composite function. So the core of this logarithmic function is composite, is a rational function. And in that case, the numerator should not be equal to 0, and the denominator should not be equal to 0, because both cases make the functions undefined. Equally, this x equals 2 and x equals negative 1 are not part of the domain of definition. So our domain is written as from negative infinity to 1. From below, then we continue with 2 from above to positive infinity. You can see that the region -1 to 2 does not exist in this domain of definition because the function is not defined in this region. So this domain is an interval notation from -infinity to -1 from below, and 2 continues at 2 from above to positive infinity. These are domain, and it has 1 bound, 2 bounds, 3 bounds, 4 bounds. So there are 4 bounds to this domain of definition. Now we look for the limits as x tends to positive and negative infinity. So let's consider this rational function inside as x is tending to infinity. X plus 1 will just be approximately equal to x as x tends to infinity. This we can replace this numerator just by x, just like we saw in limits in chapter 6 or I think 7 of the GCE math panel lessons. You can get it on the same channel. And as x tends to infinity, the denominator is approximately equal to x2. So for rational functions and getting limits at infinity, listen attentively, only at infinity. Do not do this if you are not working with the limit at infinity. So at infinity, this limit can be approximated to, for the numerator, you take the term with the highest degree, that is x. For the denominator, you take the term with the highest degree, which is still x. When you divide the two, you are going to have 1. Now the limit of 1 is equal to 0. So this will happen at positive infinity and the same at negative infinity. And since this limit is equal to 0, we can now say, or we already see that the line y equals 0 is a horizontal asymptote. Secondly, if you watch this video, make sure you solve all the exercises that you watch in this video. This is not a TV series. It is actually a lesson. This is an advice for online studies. Whenever you're studying any lesson that has to do with drill and practice online, you must be solving the exercises as you watch, or after watching, you watch again, but make sure that you solve the exercises. Otherwise, you'll just be wasting your time. This is not a TV series. This is a very important advice, which I have even talked about on other platforms. Please. Now, the limit as x tends to -1 from below, we can take a number slightly less than -1 and test here. We know that at -1, this function is undefined, so it's infinity. So the limit from below, we know that the value is already infinity. So we want to test and see if that infinity is positive infinity or negative infinity. So we'll take a number slightly less than -1. You can take -1.1. Note, -1.1 is less than -1 for negative numbers. So if we test like -1.1 and test in this function, we'll have the limit of -1.1 plus 1 over minus 1.1 minus 2. The limit of this is going to give us a negative number because the number is lying below 0 and 1. The limit of any number lying between 0 and 1 is normally negative, or this is going to give us the numerator minus the denominator, which is going to give us a negative number. Since the value is negative, we now know that the limit, which was infinity, has sign negative, because already now the limit was infinity, but we did not know the sign. Now let us also test the sign as x tends to 2 from above. Know that the region from 2 from below is not defined, so 2 from above. When we test, we can use a number slightly greater than 2. Let's take 2.1. We take 2.1, we see that the limit of 2.1 is 1 plus 1.34. This number is positive. We know that the function is not defined at x equals 2, so we know that that limit is infinity. Now we are doing this test to find out the value of that infinity, what is the sign of that infinity, which is positive infinity or negative infinity. So this gives us positive infinity. Now the next thing is the asymptotes. It is clear from the domain of definition that the equation of the vertical asymptote is the line x equals -1. This is the mistake some students make during exams. They say the vertical asymptote is -1 and -2. That is not correct at advanced level. The vertical asymptote or horizontal asymptote or whatever is a line, and a line is defined by either x equals something or y equals something. So to state your asymptotes correctly, you have to say x equals -1, x equals 2, and we already saw that the equation of the horizontal asymptotes was y equals 0. We obtain the horizontal asymptotes from limits, and we get the vertical asymptote from the domain of definition. Now that we have our limits and we equally have vertical asymptotes, from here we can discuss about the center of symmetry of this curve. A curve that has two vertical asymptotes, the center of symmetry will occur at the x value being the average of those two x values, to average of the two vertical asymptotes. So we have -1 plus 2, which is 1 divided by 2, 0.5, that's the average. And the horizontal asymptote is 0. So the center will be at 0.50. So take note of this average. Now let's get the derivative of this logarithmic function. The derivative of logarithmic function, if you have not done this, our past lessons, if you look at the past lessons, you look at differentiation, and there we have discussed logarithmic functions and exponential functions. Please just go through those lessons. Lessons are short. This particular lesson is a bit lengthy because it has a lot of important aspects that it has to be touched for further mathematics, for technical mathematics, and for general education mathematics. So that is why we are taking our time here, because sometimes students also complain that the lessons are too short for some advanced level lessons. So right, so to differentiate a logarithmic function, we have the derivative of the core divided by the core. The core here is x plus 1 over x minus 2. So the derivative is going to be given by the derivative of this core divided by the core itself. That's how we differentiate logarithmic functions, okay? That's why I've written here as f prime of x, where the core here is this f of x divided by f of x. So normally, another thing is that this core, the core here is a rational function. So we equally have to apply the quotient rule. So this will give us the quotient rule. We keep the bottom constant, always at the bottom, okay? Keep the bottom constant. We differentiate the top. We differentiate x plus 1. We're going to have 1 minus the top constant. The top is x plus 1 times the derivative of the bottom, which is 1. All that on the bottom squared. So this is just the derivative of the core. Now divided by what? By the core. The derivative of the core function, all that over the core. So when we simplify all of this, this is what we are going to have. We are going to have -3 on x minus 2 into x plus 1. This gradient function is a rational function. Rational means fraction. It's a rational function. And the numerator of this rational function does not have any variable in it. In simple terms, there is no x in the numerator of this derivative. And when this occurs, we say that there is no turning point because there is nothing for us to solve for. Okay, so there is no turning point. That's the reason why there's no turning point, because there is no x in the numerator. As students say it, trying to use student language as much as possible. Since there is no turning point, we can go ahead to our variation table. So our variation table. The variation table, the first line here, as you have seen in the previous lessons on functions, we copy the domain and paste -infinity to 1, 2 to positive infinity. And since we have two vertical asymptotes, we are going to put solid lines under these values of x that gives us the vertical asymptotes. So the vertical asymptote occurs at -1, another one at 2. And the function is not defined in this region between -1 and 2, as we are going to see. All right, before we come to that, now let's look at the monotonicity of this function between -infinity and -1. It means we want to look at the increasing and decreasing behavior of this function from -infinity to -1. That's it, or you can equally call it the sign of the gradient function. So let's take any number between -infinity and -1. You can take 2. No, 2, -2, I'm sorry. If you take -2 and fit in this and substitute in this gradient function, we'll have -3. All the numerator is negative. The denominator, it is going to be negative times negative, which is positive. So negative divided by positive gives us negative. So the function is decreasing in this interval. And then the region between -1 and 2, what is happening to the function? The function does not exist here. So we don't study the gradient function there. How can we study something in the region where the thing does not exist? So we can only study the variation the limit, the region now from 2 to positive infinity. And it's also negative when we test using any value greater than 2. Okay, take any value greater than 2, you have the numerator to be negative and the numerator to be positive. Now, in this region, since it's negative from -infinity to -1, the gradient is negative, shows that the function is decreasing. So this function is decreasing from which value to which value? As x tends to negative infinity, what's the value of g of x? You can see that at limits, it's 0. And as x tends to negative 1 from below, we can see that at limits, it's negative infinity. Whenever you make a variation table, negative infinity must always occupy these positions down. It must be down, whether it's here at this corner or this corner, it must be down. And whenever there is positive infinity, it must be at this upper position. Whether it's at this position to the left or to the right, it must be up. Because negative infinity is the smallest value that should exist. From what we have observed from past exams too, is that sometimes the function increases negative infinity. How can something increase to something that is the smallest thing that exists? It's not possible. So something can only move down to that thing, or something moves from that thing upwards. Okay. Okay. Now, equally in this region from 2 to positive infinity, the function is also decreasing from the gradient function. The limit as x tends to 2 from above, you can equally see that at limit it was positive infinity. Now you see where positive infinity is going to be. Positive infinity must always be up. And as x tends to positive infinity, what is the value of g of x? You can see that at limit again, 0. Now, another thing is this: if they just gave me only this variation table and say I should state the equation of all the asymptotes, I can see it from this table. Look at the limit as x tends to infinity, negative infinity. You have 0. So this means the value y equals 0 is a horizontal asymptote. And equally, if I look from this right, I'll see the same thing. The limit as x tends to positive infinity is 0. You can still see the horizontal asymptotes from there. So your variation table has to match with what you have already checked with the limits, the domain, and whatever. All of them match. And it must also match with this gradient function. Otherwise, you'll just be doing jazz. Please, I'm sorry for saying this, but you just be doing jazz. Another thing we notice is that the function does not exist in this region from negative 1 to 2, as we saw in the domain of definition. You can see the match, right? It does not exist in this region. So it is not possible that I should have anything to study here. Even the gradients, there is no need to look for any gradients there. So you can see that you should state the region where the curve does not exist, and it is the region from x greater than negative 1 and less than 2. You can see if you give the monotonicity of the function, the region negative infinity to negative 1, it is decreasing strictly. 2 to positive infinity is also strictly decreasing. Now that we have variation table, you can check if you have some intercepts. Okay, check if you have some intercepts. All right, some remarks. The curve does not cross the axis and the HA. We are going to see that this curve does not cross the horizontal asymptotes, and it does not exist in this interval, as I've already mentioned. The center is the average of the two VAs for the x value. The domain is different. Look at this point. The domain will be different if brackets are used. I mentioned this at the beginning of this lesson. And if we change to absolute values, you also see some changes that will occur. So let's sketch our curve. Now this curve, normally we have the intercepts as well. X tends to 0. But from here, the curve will not be defined. The x value does not exist in the domain of division, so we cannot talk about when x is equal to 0. That's why I don't have any intercepts here, because look at it. The domain says that x can never be 0. So I cannot say when x equals 0, what's the value of y? All right, but we can equally talk about if y is equal to 0, then what will be the value of x? Okay, but now further information needs to be given with that, because if y is equal to 0, then we are going to have e to the power 0, which should be equal to that. And when we solve here, x is going to be negative 1. And this x being equal to negative 1, the function is also defined when x is equal to negative 1. That is why the intercepts have not been given in this question, because the 0 and the 1 values of x do not exist, or the function is not defined for those values. So here we have our horizontal asymptote line y equal to 0, which is a broken line. We have two vertical asymptotes, one at x equals 2 and another one at x equals negative 1. Then from the region from negative infinity to -1 from below, the curve is decreasing. So this is what we have. And from 2 from above to positive infinity, it is also decreasing. So we have these lines you have indicated here and here. You can now link those lines like that. And this one. So this is the curve of this function. This is the curve of this function. Okay. Hey guys, so stay tuned and watch all the other videos in this particular presentation, and that's really going to be awesome. Okay. All right, so these are my labels. The curve of G. You can always visit our website www.gcemathpanel.blogspot.com for more information, or you can go to the GCE Preps platform, www.gcepreps platform. GCE Preps platform is one word and all the letters are lowercase. www.gcepretsplatform.blogspot.com. You have lessons there that are really going to help you as you prepare for your exams. All right, now we take the next function. So here we are going to look at that same function, but now with absolute values. Can you see it is the same function now with absolute values in this case? And you see how the curve is going to look like. Initially, in the past question, it does not exist in a particular region, but now let us see what is going to happen for that same curve. Don't forget to subscribe to this channel, and you can visit our blog www.gcemathpanel.blogspot.com, where we have a lot of material there for you. You can follow us on Facebook, GCE Math Panel on Facebook, and you can equally follow us on Twitter. So guys, now we look at that same function here in the case where we have absolute values. So with this same function, let's see how we get the domain of this function when this call exists as an absolute value. We know that the absolute value of a number makes the number that is negative to become positive, and the number that is positive remains the same. So with this function, the domain will be possible if this numerator is not equal to 0 and the denominator is not equal to 0, because the only thing that will stop us from having this function being defined is if what you have inside this a call inside this absolute value is equal to 0. So the domain for the same function when brackets are used is different from that same function when we now have absolute values replacing those brackets. So you now see what happens to the domain. Because if a value is not, if the numerator is not 0, is equal to 0, and the denominator is not equal to 0, any other value for this function will make this function defined. Why? Because of this absolute value. So the domain here is strictly x minus 2 should not be equal to 0, and x plus 1 should not be equal to 0. So the domain is now given by from negative infinity to 1, negative 1 from below. Then we continue from negative 1 from above to positive 2 from below. Then 2 from above to positive infinity. So only the exact values that are not defined for this function are x equals 2 and x equals negative 1. So when we had brackets, we had how many bounds? We had 4 bounds. Now, how many bounds are we having? We have 1, 2, 3, 4, 5, 6. This is now telling us we have to look for 6 limits at the bounds of the domain of definition, because now have 6 bounds. Now, the same limit we had previously applies here. Since this is a logarithmic function with a rational core, working with this rational function, we just have to take the term with the highest degree divided by the term with the highest degree. This only applies to limit at infinity. I am repeating this because sometimes students listen, but they don't hear, but they don't listen. So this only applies at infinity. Take highest degree divided by highest degree only when you're looking for limits at either positive infinity or negative infinity. So get this right. So here I'm taking the highest degree divided by highest degree. And the limit of that is going to give me 0 because that will give me 1. At positive infinity, I will have ln 1. At negative infinity, I'll still have ln 1. Okay, now the limit as x tends to -1 from below, we know that the function is not defined at x equals -1. So we want to find the sign of this limit. We already know the limit is negative, is already infinity, sorry, but we need to know the sign, whether it is positive infinity or negative infinity at -1 from below. So let's take a number slightly less than -1. We can have -1.1. So when we test, it gives us a negative value. So that limit is negative infinity. Okay, so the absolute value here, it's a positive number, but that number lies between, if that number lies between 0 and 1, the lim of a number that lies between that 0 and 1 should normally be negative infinity. Okay, now let us look at the limit as x tends to -1 from above. Now note that the function exists in this region. So we take a number slightly less greater than -1, we can have -0.9. Note, -0.9 is greater than -1. -0.9 is greater than -1. You can check on the number line. So this gives us the lim of -0.9 plus 1 or -0.9 minus 2. And this limit is going to give us negative infinity as well, because the value we obtain here is that same number which is lying between those, whatever you can test the calculator, you call it that. Now limit as x tends to 2 from below, the number slightly less than 2, we have 1.9 we can use to test. We obtain positive infinity. And 2 from above, we have the same value I had previously. We used 2.1 to test, and we have positive infinity. So from here now, we can look at our vertical asymptotes, the same vertical asymptote like before, x equals -1, x equals 2, y equals 0. And this is the center of symmetry. Now, our gradient function will remain the same. The derivative of a logarithmic function is the derivative of the core divided by the core. The core function here is x plus 1 over x minus 2. So divided by the core. Okay. So this is what we have. The derivative is the same. Now we have these other points. The gradient functions as well, the same. This is a vertical asymptote. So, and x equals 2 is another vertical asymptote. We can check the sign of the gradient in these regions. We have the same values like before, but the only difference here now is that since the function exists in the region -1 to 2, when we test using any value between -1 and 2, we use 0, for example, the function is going to be increasing in this region because the gradient function will be positive. Okay. Now in this first region, the gradient function tells us the curve is decreasing from what value? As x tends negative infinity, what's the value of g of x? We can start at limits. As x tends negative infinity, g of x tends to 0. As x tends -1 from below, limits tends to negative infinity. As x tends -1 from above, we have negative infinity. 2 from below, we have positive infinity. That's 2 from below, sorry, and 2 from above, 2, we have positive infinity, and the curve is decreasing in this region. That's from positive infinity to 0, because as x tends to positive infinity, y tends to 0 from limits. So we now have a table of variation. Here, a remark is that we can look for the intercept here because the curve exists in this region. So when x is equal to 0, there is actually a value of y when x is equal to 0, unlike when we had brackets for the same core. So this is the difference between rational logarithmic functions or logarithmic functions, the rational core, which has absolute values, and in the case where we have brackets. So for the first intercept, when x is equal to 0, and we substitute in this function, we are going to have y to be equal to negative ln 2. Because we have 0 plus 1, which is 1, all over 0 minus 2, which is negative 2. The absolute value of this is going to give us the ln of a half. And ln of a half is the same as ln 1 minus ln 2, which is ln negative 2, because ln 1 is 0. Then there's another intercept. When y is now equal to 0, when y is equal to 0, in the chapter 1 of these lessons from the GCE math panel, we did this logarithmic function. So if y is equal to 0, this is the value of x we're going to have. So in that case, we're going to have the absolute value of x plus 1 over x minus 2 to be equal to e to the power 0, which is 1. And when we solve that curve function, we are going to have this intercept. If you have issues with this, please go to chapter 1, where we have absolute value equations. You see on the absolute value equations how we solve this. Okay. So when you solve, there are normally going to be two values. For the first value is not going to make sense, so there's the value of x is not going to exist because the x will cancel out. But for the case with the negative now, it's going to exist. So we have two intercepts, okay, at these points. So we can now sketch our curve. This is a horizontal asymptote. It has two vertical asymptotes, and the curve is decreasing in this region up to negative 2 from below, the same like the previous curve. And the region 2 from above to positive infinity is decreasing as well. So we have these two lines, this line and this line, to indicate. And as x tends to, all right, these are the points here. Now with this region between, this is what we're going to have, the curve. Note that as x tends to 2 from below, we had negative infinity at limits. 2 from below, we had positive infinity. This is the positive infinity here. And as x tends to minus 1 from above, we had negative infinity. This is a negative infinity here. And according to the intercept, this curve passes through the points 0, negative ln 2. This is the point here. And also passes at 0.50. X is 0.5, y is 0. So we link all of these points, and this is what we have. So this is this same curve in the case now where we have the ln of absolute value. There are 4 other logarithmic functions. So this is part 1 of this video. I will implore your indulgence to watch the other 4 as you saw at the beginning of this lesson. So stay tuned, and this is the GCE math panel. As an advice, watch these lessons and solve. If you finish watching them, you solve, or you solve while watching, because this is not a TV series, it is a lesson. And as advice for online lessons, like a tutor who has been teaching online for long, drill and practice subjects like mathematics, physics, chemistry, and so on, they require that when you watch them, you also do the solving or the practice. Okay? All right, thank you so much. So this is going to be the next function, and please, you watch this on our channel. Stay tuned, and bye-bye.